Hello everyone, welcome back. In this video we'll be talking about density computation for metals. Now we explain the crystal structures or the commonly crystal structure that happens in metal: simple cubic, body centered cubic. We said we're dealing with cubic crystal system. Then we said face centered and hexagonal closed pack. We explained the four of them, the way the atom arrange themselves within the crystal structure, the relation between the unit cell edge and radius of atoms, and we explained how to calculate the volume of the cube based on the radius of atom, and also we explained the relation between A and R, an atomic packing factor. Now, if we know the crystal structure of a metal, we can calculate its theoretical density. Now, you know from physics or chemistry, you can go to lab and calculate density practically. You take a sample, you measure its weight, you measure its volume, then weight over volume is going to give you density, which we know with mass over volume. This is what we know. Density is equal to mass over volume. Now, how can we use this equation and change it to an equation that we can use crystal structure? If I know a crystal structure of a metal, I can calculate its theoretical density. Now, the equation that we're going to use, we're not going to use mass over volume directly. Well, you can. If you don't want to use this equation, you can still use this equation, but you have to go through the conversion which is already placed here. Now let me just divide this equation into two parts. This is one part and this is the second part. Now imagine we have a cube, and we want to calculate density for this cube. Sorry, should have been a nice cube if I can draw. So let's say we have a cube here, and we want to calculate density for this cube. Remember, for calculating density, you will make one of them constant. It's easier for calculation. So here we'll stick to a cube. We have a cube which the side will be A. Now I can calculate the volume of this cube. So VC stands volume of the unit cell that we explained, volume of unit cell. Now the other part that we want to know the atom weight or the atom mass within this unit cell. Now this should recall the number of atoms within each unit cell. We said for simple cubic, the total amount of corner atoms was equal to one atom. So it means that if this is simple cubic arrangement, I can calculate weight of one atom, and weight of one atom divided by the volume, it will give me density. If this is BCC, we know there is two atoms, so I need weight of two atoms. If it is FCC, it will be 4 atoms. So how would I calculate mass of atom in that case? Mass of atom, well, this is what we calculate mass of atom. Now, let me explain this one to see where does this came from. Very simple. We know that, look, we know first atomic weight. Let's bring the thing that we need them. The thing that related to weight, we have it, is atomic weight, that will say gram per mole. let's say gram per mole. We explain this one. So 1 mole of that element weight that much gram. So let's say A is 50 gram per mole. We know that 1 mole of that element is weight 50 gram. Well, I don't want a mole. I want what? I want 1 atom. I mean the weight of 1 atom. Why? Because if I know the weight of 1 atom, then if it is simple cubic, I'll multiply it by 1 because I know there is 1 atom inside it. If it is BCC, I'll multiply it by 2 because there is 2 atom. If it is FCC, I'll multiply it by 4 atom. Why? Because there are 4 atom inside the BCC crystal structure. So I need to calculate the weight of 1 atom. Well, I have the weight per mole. What does per mole means? That 1 mole of this element weighs 50 gram. Let's say 50 gram, we'll say it here. That's an example. Make it number, will be easier to understand. 50 gram. Well, the relation between mole and atoms will come Avogadro number. And we know that in Avogadro number, Na stands for Avogadro number, we'll say that 6.022 10 to power 23 atoms per mole. Going to be atoms per mole. Now, this allows me to calculate or find the relation between atoms in a mole. Now, what does this mean? If I have 1 mole of that element, I have this much atoms inside it. And we know that 1 mole is 50 grams. So what does it mean? It means that this much atom, they weigh 50 grams. Why? If you just simply write it somewhere. So let's write this one somewhere here. We'll say that 1 mole is equal to 50 gram. And I know 1 mole is equal to what? At the same time, I know 1 mole has Avogadro number. If I can write it here, 6.022 10 to power 23. Now, I can just simply substitute because 1 mole has this much atom and 1 mole also weighs 50 gram. So what does it mean? It means that this amount of atom together they weigh 50 gram. I mean, it's the way that to say that, let's say that Ahmed is Jack's brother and Ahmed is, that's another name, is Jonathan's brother. So in that case, Jonathan will be Jack's brother. So because 1 mole is 50 gram and 1 mole has this much amount of atoms, so this much amount of atoms, they weigh 50 gram. This is, we know in mathematics, this is how we have similar theorem in mathematics. If A perpendicular to C and A perpendicular to B, then A is perpendicular to B, A is perpendicular to C, so B and C, they're parallel. There's a theorem like this in mathematics in high school. So it's similar. We say 1 mole is 50 gram and 1 mole has this much amount of atoms, so we know that this much amount of atoms, they weigh 50 gram. Well, now you realize that I don't need that much amount of atoms weight, I need 1 atoms. So we write it in this manner. We'll say, okay, now we got the point that if 6.022 10 to power 23 atoms weight 50 gram, then we need 1 atom weight, so we're going to put X here. Why? Because I need to know the weight of one atom. So if you realized here, if I can change this one back to the letters, this 50 was atomic weight, and this is Avogadro number. So if I want to find the weight of one atom, we'll say what? We're going to find X here. X will be 1. If this one will be number of atom, let's say put N. So N times A over Avogadro number. Now you realize how the equation written there, Avogadro number. So this is nothing, it's just the mass of the atoms, and this is the volume of the cube that we have there. Now you don't need to go through this process in order to calculate atom weight. We'll directly use the equation there, but you have to know where does this equation came from. The base is still mass over volume, because when you say density, it is still mass over volume. So the mass of atoms here, this is the part of mass of atoms, N, which is the number of atom times, because here you do the same calculation, and you're going to get X. Let's say number of atom times atomic weight over Avogadro number is going to give you the mass of atoms. N here stands for number of atoms, it's written here, number of atoms associated with each unit cell. A will be atomic weight, Vc is the volume of the unit cell, and Na Avogadro number. Now this is the base equation that we're going to use for density computation. Now, let's see how do we use this equation in the calculation. Excuse me. Sorry. No. Now there's mainly two-way or three-way to use this equation. Three main categories we have within the calculation. First is just simply we calculate theoretical density, we call it. Theoretical density of metal. Remember chapter 3 we're mainly working with metals, so whatever we have it here, single element. In chapter 4 we're going into alloys. Now maybe one of you is asking, okay, how do we calculate density of alloys? If you have more than one element, sure, we're going to talk about this topic as well in chapter 4. Well, here we imagine we have one element. So we said we can use this equation as a base for calculating theoretical density. Now, theoretical density should be very close to the practical density, the actual density of the material. Remember, this is a theoretical we're calculating, but it should be close, very, very close to the actual density of a metal. So if someone asking you to calculate, telling you, okay, how much is the density of aluminium, you don't need to go to the lab to calculate it. You just have a table, you know the Avogadro number, you know the atomic weight of aluminium, you know the crystal structure of aluminium. That's it. You can calculate it as density. By the way, let's just show you the, if I can have this table. I'll share that. Okay, there's a table here. Now we're going to use this table, and they're called characteristics of select elements, not all of the elements, selected elements. What do we have there? We have their symbol, atomic number, atomic weight, density, crystal structure. So look at the crystal structures here. The crystal structure can be used if I know the crystal structure and I know here atomic weight. For example, if I don't have the density, I can theoretically calculate the density. Why? Because I just need the crystal structure, atomic weight, I know the rest of the things. so I can calculate this density. Now this is one way to use this equation to calculate theoretical density. I shall show it to you in some examples we have it. Now the second type of problem that we can use this equation is question related to the crystal structure. Now you might know the density. Let's say you have a metal, you know the crystal structure by a technique. Let's say you found the crystal structure. Now you want to find the radius of the atoms. Imagine you have a metal, you took it to the lab and you perform type of experiment we shall teach you in the end of this chapter, and then doing some calculation you found the crystal structure and you measured its density. By having the crystal structure and density, you can find the radius of that atom. I mean, theoretically, you can, to see whether your findings match the one that within the table. Remember, you have that. If you know the elements, someone may ask, okay, why do I have to calculate radius when if I know the element? Sure, you know the element. The radius is already given. Atomic radius, you have it. Atomic radius is given. But sometimes we have to check to authenticate the finding that we have it. So we have to check to see whether the thing that we found in the lab, does it match what we know about this element? So in this way you can use this equation to find atomic radius, some relation to the crystal structure. This is another way. There is a third one can be used to identify crystal structure. Let's say you have a density of the material. You want to identify the crystal structure. So how would we know which type of crystal structure we have it? Let's say it's simple. If someone is telling you that this is iron and this is the density of iron, which crystal structure does the iron has? A simple question is, I can use this equation as well to calculate crystal structure. We shall show you 3 calculations to see how we're going to deal with each of them, especially the third one, which is finding crystal structure. There's different approaches that you can use to identify the crystal structure. Now let's start with the simple one, at least to get used to the units, to see what we have there, the units to be clear. Then we'll go for the other ones. I think I will create another video so the videos will not be long. So in the next video we're gonna do some calculation on the density computation, simple calculation. Then we're gonna go for relation with the crystal structure. Then the third part, which is finding crystal structure. Thanks for watching.